This is lecture 20 of numerical methods. As you can see, it's about something called Newton's divided differences, a method for interpolation, and his forward difference formula. Here in 2020, spring of 2020, because of the coronavirus pandemic, we've been doing things online, and we've been doing function interpolation. Lecture 18 was about Lagrange interpolation. Lecture 19 was about a real tricky method called Neville's method. Lecture 20 here, Newton's divided differences method, is also pretty tricky. So you're going to want to definitely have a piece of paper, calculator, pencil handy. Pause the video, double check calculations as we go. You'll get a lot more out of it if you do that. Before we get into the content, let me also briefly say what to expect of the rest of the semester. I'm not going to quite finish section 3.3 in this book. This is our textbook here, Numerical Analysis, which is about Newton's divided differences and the forward difference formula, because it also contains something called the backwards difference formula, and it just seemed like too much to include all of that in this lecture. So I'll finish section 3.3 in lecture 21, and also do some more in chapter 3. We're also going to do Hermite interpolation, probably in part of lecture 21. Cubic spline interpolation for lecture 22. I'm going to do those fairly lightly. We could go into a lot of depth about those, but I want to focus on the main idea and using technology for those things. Then I'm going to move into chapter 4, talk about the fundamental aspects of numerical integration. I'm not going to do a ton of detail there because I want to get to chapter 5, which is on numerical approximations to solutions of differential equations, in particular things called initial value problems. And we're going to look at applications of those things. That'll be the most significant thing you can get out of this course as far as future applications, I think. Here's the plan for lecture 20. Newton's divided differences, just like Neville's method, is best talked about in the context of an example. So we'll start with an interpolation for 3 data points, and we'll get an interpolating quadratic function. In fact, it's the exact same 3 data points as in Neville's method from lecture 19. I'll do a quick review of Lagrange interpolation, but I will not review Neville's method. I'll talk about the big picture idea of Newton's interpolation method. Then we'll carry out the details for the example, which is not too hard. Where this gets harder is when we try to generalize it to more data points and talk about the method using these things called divided differences and the special notation that comes with this. Part of the difficulty in all this is dealing with the notation. Okay, so that's something to be aware of. We'll talk about carrying out the implementation of the method in a table by hand with calculator help and also in a spreadsheet. We'll add a 4th data point. And in fact, it's this addition of extra data points which makes this method pretty nice in some ways. We can do it pretty nicely by updating the table either by hand with a calculator to help you or in a spreadsheet. We'll focus on the most important part of the table is called the upper diagonal. You'll see what I'm talking about when we get there. It turns out, by some properties that you can verify algebraically, though it's messy, that the order of the nodes does affect the numbers in the table, but not the final answer, not the final polynomial, and not the final approximation, when you simplify things at least. Okay? It does affect the intermediate calculations though. Make some other general comments about divided differences. In fact, I'll say one here. It turns out the nodes don't even have to be in order from least to greatest. And also, they don't have to be equidistant from each other, though our examples will be. It is nicest when they are, but they don't have to be. It's nicest especially in terms of Newton's forward difference formula. We'll talk about that in terms of divided differences. You can write it really nicely. And we'll also briefly talk about something called the forward difference operator. My students have seen this before spring break. It's the capital delta notation that we used. In lecture 21, I will get into more details about that. All right, let's get into our example. So this is the exact same example as in lecture 19 with Neville's method. We've got 3 data points, 0th data point, a first data point, and a second. That's really 3 data points then. The 0th node is 2, the first node is 4, and the second node is 6. And the corresponding outputs of the function are 5, 6, and 8. We're assuming those are exactly known. This is best approached when you're not dealing with noisy data. Okay, so you assume you've got exact values. You're also really assuming the function, the underlying function, is fairly nice. either because you know what it is, like the sine function, for example, from lecture 19, or because you have a physical reason to know the function's nice and well behaved. It's not oscillating wildly in between the data points. Okay, it's a pretty nice function. That will help us achieve our goal of estimating 4.5, f of f 4.5 pretty well. 4.5, notice, is interpolation. It's not extrapolation. It's between 2 and 6, the lowest and biggest nodes. Let p of x be our answer, our unique quadratic interpolating polynomial for these data. In general, when you've got 3 data points that are not along a straight line, there will be a unique quadratic that interpolates them exactly. Lagrange interpolation is the idea of writing these things as a linear combination of some quadratics. What quadratics are they? This one, and this one. Excuse me. Here's the key idea. Notice this quadratic is 0 at the nodes 4 and 6, and equal to 1 at the 0th node, which was 2. You plug in x equals 2, you get 1. This one right here is 0 at the nodes 2 and 6, and 1 at the middle node, x equals 4. And this one is 0 at the nodes 2 and 4, and 1 when x equals 6. And the weights or coefficients in the linear combination, 5, 6, and 8, are the outputs there. And those numbers guarantee that this will give us the correct outputs at the nodes. We exactly interpolate the data. It's a little bit of a pain, but not too bad in this situation to simplify this to this. In more general situations where the numbers are not as nice, like with the sine function, the weights are not as nice, it's not so pleasant to simplify it, though certainly doable. In this case, it simplifies to 0.125x squared minus 0.25x plus 5. It's worth taking the time to write that down now, because I'm going to refer to it later. Okay, so you want to have that written down. The coefficients are 1/8, -1/4, and +5. That'll be worth remembering. Then we plug in x equals 4.5. We interpolate and get an approximation for f of 4.5. In exact form, it's 6.40625. Though you should keep in mind that if you're talking about a real-life application here, depending on how much precision you have in your data, you'd want to round this to a certain number of significant figures, maybe 6.4 or 6.41. And again, this is a linear combination of quadratic terms that are either 0 or 1 at the appropriate nodes, and here's the graph. The red graph is the quadratic interpolating polynomial. The 3 black dots are the data. The green dot is where we're trying to approximate the function at 4.5 to get 6.40625. Got this funny notation, P012, that came from Neville's method, okay? I'm not going to use that notation again. Essentially, the 0, 1, and 2 emphasize that this is a quadratic that interpolates exactly at the 0th, 1st, and 2nd nodes. Don't worry about it. Again, here's the answer. Remember that. Write it down. How is Newton's method different? Newton interpolation writes p of x in a different form. Not in that same linear combination as before, but a new linear combination, actually. A0, which you can think of as A0 times 1, if you like, plus A1 times x minus 2, plus A2 times the product, x minus 2 and x minus 4. A 0th degree term, a 1st degree term, and a 2nd degree term. You can think of 1, x minus 2, and then x minus 2 times x minus 4 as being 3 polynomials that form a basis for the vector space of all quadratic functions. If you don't know what that means, don't worry about it. And this is a linear combination of those. Of course, you got to solve for the AIs. And I hope it makes intuitive sense that that shouldn't be too hard to do. Plug in your data points. And in fact, this is set up to solve nicely for A0, for example, when you plug in x equals 2, because these become 0. And also then for A1 when x equals 4, because this becomes 0. And that's what we're going to do in the next slide, in fact. It's a linear combination, again, of a constant, 1, a linear term, x minus 2, and a quadratic term, the product of x minus 2 with x minus 4. And the linear and quadratics are 0 at the appropriate nodes, which makes it easier to solve for A0, A1, and A2. This also has some other benefits. Once the coefficients are found, if you have to do a lot of computations with this thing over and over again, it can be more efficient computationally than in its standard form, you might say, because of its nested nature, especially when you get to higher degree polynomials. This is especially the case. This is the nested form. Notice I factored out an x minus 2 from both of these terms to get this. And it is nested. You would work from inside out when you plug a number in for x. You could first subtract 4, then multiply by a2, then add a1. And then after subtracting 2 from x, multiply here and here, and finally add a0. And again, this definitely has benefits when your polynomial is higher degree. And the method also lends itself well to adding on more nodes. It's easy to add new terms in the spreadsheet with new nodes. Though remember, if you do add new nodes, in general, it's going to become higher and higher degree, third, then fourth, then fifth, and sixth degree, etc. But then the nested nature really comes into play in a handy way. Okay, let's go ahead and solve for the AIs. Starting with A0, just like I mentioned a minute ago. Go ahead and plug in the first node x0. Here, here, and here. That gives you p of 2, which we want to equal f of 2, which is 5. These two terms become zeros, so a0 must equal 5. a0 must equal y0, which is f of x0. It is the function value at the first node. That does happen to equal the constant term in the simplified form, which I told you to write down. Remember, the quadratic was 1/8 x squared minus 1/4 x plus 5. 0.125 x squared minus 0.25 x plus 5. The 5 happens to match the original 5. That was just by chance. Okay, that's not usually going to be the case. Think about it here. If you think about the previous slide, the constant term is not in general going to equal a0. It's going to equal a0 plus a1 times this thing plus a2 times the product of these things. That does just happen to equal 5 in this case. A0 just does happen to equal the constant term. That doesn't happen in general. A1 is definitely not in general equal to the coefficient of x, which was negative 1/4. It ends up equaling a 1/8 and 1/2 in this case. We can solve for it by plugging in x equals 4 here, here, and here, making this term 0. So we can solve for a1 to be 6 minus a0, then divide by 2. That's what we do here. 6 minus a0 divided by 4 minus 2, which simplifies to this. a1 is 1/2 or 0.5, not negative 1/4. Okay? In general, they should not be the same. What's this stuff in the middle? That is a divided difference. It's called a first divided difference. Why? Because this is a division of two differences. Very similar to the idea of a difference quotient back in calculus. Though in calculus, you take a limit of a difference quotient to get a derivative, slope of a tangent line. This would really be a slope of a secant line, an average rate of change between x0 comma f of x0, which is 2, 5, and x1 comma f of x1, which is 4, 6. Okay, and that's what happens here. But it is a divided difference. This is just alternative notation for the divided difference. It will be handy notation, but this is one of these weird things that takes some getting used to. Okay. Finally, solve for a2. Plug in x equals 6, the second node. Sorry, blow my nose here. I have bad allergies. Plug in a2, or plug in 6 for x. Here, here, and here. Solve for a2. You already know a0 and a1. We can solve for a2 by subtracting this from both sides, subtracting this from both sides, and then dividing both sides by this. And the answer is 1/8, 0.125. That does equal the x squared term for the answer. Is that by chance? No, that will happen always with 3 data points in quadratics that are interpolating. That number a2 will be the x squared term. Think about it here. Go back here again. The x squared term can only come from a2 times this times this. Okay? So it will equal what we got before, 1/8. Again, this one, the 5, was just by chance. This one was just by chance that it equaled the constant term. All right, now is where it gets hard. Okay, take a breath. I need a breath too. I need a drink too. let's use some fancy algebra. And I do mean fancy algebra, unexpected algebra, crazy looking algebra, you might say, to rewrite this in a way that will generalize. It's not at all obvious a good idea of what I'm about to show you here. Okay? But it is important if you want to really get Newton's divided difference method. It is important to understand this algebra. First step is to write A2 in this way. Now, this is pretty crazy looking, although it is just a generalization of what I've got right here. Think about it here. 8 is f of x2 because x2 was 6 and f of 6 was 8. Minus a0 is the same as minus f of x0. a0 does equal f of x0, f of 2 in this case, which is 5. Minus, okay, we've got a 6 minus 2 here. Also have an x2 minus x0s. x0 is 2, x2 is 6. It's the same thing. And then we have this thing. Hey, that looks like a divided difference. That's this thing, which equals a1. Just like we have here, we're subtracting a1 times this. This is a match. This thing I circled down here is equal to a1, which is a half for our example. Then all divided by x2 minus x0 and also a factor of x2 minus x1, which matches 6 minus 2 and 6 minus 4. So this first step, though messy looking, is nothing more than a generalization of this. The next 3 steps, especially the first and second next steps here, are extra tricky. I'm going to write this. Are these really equal? Yes, though it takes some time and skill with algebra to see it. Certainly the denominators are the same. x2 minus x0 in parentheses times x2 minus x1 in parentheses in both spots. Certainly this f of x2 is the same in both spots. Well, what about the rest of the numerator? Where does this negative f of x1 times this fraction here come from? It comes from taking this part of this fraction here, if we split that fraction apart into 2 pieces, which we could do, times this, along with a mathematician's favorite trick of adding 0 in a certain way, in a convenient way, though it's not obvious that this is convenient. I got a plus x1 and a minus x1 in there. Notice this part with the minus sign right here is essentially the same as what I circled over here, including the minus sign. Got the minus sign, you got an f of x1 there, you got an x2 minus x0 in the numerator, and x1 minus x0 in the numerator. Those match. And again, this is not affecting the fraction. So these things are equal. What about the last term here? That comes evidently from this term here and combining this part of this fraction, including the minus sign out there, times this. Take a breath. The negative f of x0, where does that match over here? That matches this times this, really, because what I'm circling here simplifies to negative 1 when I break it apart, matching the negative sign over here, and times f of x0. And this part, f of x0 times this one here, matches these 2 negative signs cancel to give you a plus f of x0 times x2 minus x0. That's what we've got. Let me go to the next slide and come back to this one so my marks are erased here. Yeah, there we go. Okay. Now on to the next equality, which I think is even trickier. It seemed to me that this was the best way to simplify this. I mean, theoretically, you could go from this step to this step right away, but it seemed best to me to initially do this before going here. But it's not obvious that these two things are equal. Once again, we still have the same denominators, and we still have a quantity that matches here and here. But now what I've done is I've taken the f of x1 term that is in one spot here and broken it apart into pieces again. So almost seemingly undoing what I did before, but not exactly. Got that piece there, and I got this piece times this one here. And notice it is tricky. I mean, you might think, can I go from here to here? Well, you might think so initially looking at it, but notice that the x2 minus x0 is not the same as the x2 minus x1 here. So it's not obvious that these would be equal. And how I got from here to here with the f of x1 term is I essentially broke this fraction apart into this piece and this piece. And this piece, the second piece that I circled, is a 1 essentially. Then with the minus sign becomes a -1 like you see there. And the other part with the minus sign in the f of x1 becomes this part times this part with the minus sign. And then the f of x0, coming back over here, I can cancel the x0s here and here. And I have x2 minus x1 divided by x1 minus x0 times f of x0. That's matching this, and we get a plus because it's two minuses. This minus here and this minus there. Wow, really tricky. Finally, the last step's not quite as tricky. I'm going to take this x2 minus x1 and bring it up into the numerator. It's going to cancel with this x2 minus x1 in this part, and then I'm just going to put it below this thing here to write it this way. And this now has the benefit of being a divided difference of divided differences. This is a divided difference. This is a divided difference. These are both first divided differences. Notice then I have a difference of those two divided differences, and then I'm doing another division. It's a divided difference of divided differences. It's a second divided difference. The things I circled up here, I can use this notation for here and here. A2 is also a divided difference. It's a second divided difference. Notationally, the square brackets are called, the things in square brackets, involving square brackets, are called divided differences. We can even have zeroth divided differences. These are not literal divided differences. These are actually function values. We're inside the square brackets. We have just a single number. We define these zeroth divided differences to be the same as the function values. Why? Because then when we define the first divided difference, we can really define those with function values. And I could use the square bracket notation here, here, and here in these spots as well, if I wanted to. Okay? So these are the function values. These are the first divided differences, 0.5 and 1. Notice the 0.5 is the same as the A1. That was 1/2. What about this 1? Well, that didn't appear as A0, A1, or A2, but that 1 is necessary for finding the second divided difference, which will give us A2. This notation is for a second divided difference. It's a divided difference of the first divided differences, which we can write like this. And the 1 comes into play, minus 0.5 divided by x2 minus x0, not x2 minus x1 or x1 minus x0. It's x2 minus x0, which is 6 minus 2, which is 4, giving us 1/8, 0.125 for the A2. This was equal to A2. Okay, so the A1 was equal to, A0 was equal to 5, A1 was equal to 0.5, and A2 was equal to 0.125. The 6 and the 8 and the 1 are just helpers to help compute these other things. It's good to organize this stuff into a table or a spreadsheet like this. And I'm purposely putting a little space in some of these, like here, here, and here, because it just is helpful for thinking about organizing the table. So these are my nodes, 2, 4, and 6. These are our zeroth divided differences, which are really function values, 5, 6, and 8. Here are our first divided differences. There was the 0.5, there's the 1, and here's our second divided difference, the 0.125. And the numbers on this upper diagonal, from upper left to lower right, are the a0, a1, and the a2 the coefficients of the interpolating polynomial in the Newton form? Not the coefficients of x squared, x, and the constant term when you simplify it, though the x squared term coefficient will be the same as a2. Check that these numbers are right. Take the time to use your calculator to check that these numbers are right. But this 0.5, do 6 minus 5, which is 1, all divided by 4 minus 2. 1 divided by 2 is 0.5. Is this 1 right? Take 8 minus 6, 2, divide by 6 minus 4. 2 divided by 2 is 1. And finally, the 0.125 is 1 minus 0.5. It's a divided difference of first divided differences, divided by 6 minus 2. 0.5 divided by 4 is 1/8, 0.125. Does have a similar kind of feel as Neville's method. Not exactly the same. The table's structured a little differently, different notation, different terminology. And you might remember from Neville's method, we did a subtraction in the numerator as well as a multiplication. Here we're just doing differences and then divisions. Yes, and the numbers along the upper diagonal are, from the upper left to middle right, the ones I circled, are the coefficients of p of x in its Newton form. A0 is 5, A1 is 0.5, A2 is 0.125. Notationally, though, we don't have to write those divided differences in their form that would be as fractions that you can see, fractions within fractions. We can very efficiently write down the formula for p of x in this way, this abstract way, based on the nodes x0, x1, and x2. F of x0, the zeroth divided difference, is the constant term. Here, in this form at least, it's not the final simplified constant term. This is the coefficient of x minus x0 in this form, and this is the coefficient of x minus x0 times x minus x1 in this form. Again, this will be the same as the quadratic coefficient for interpolating 3 points. Let's now add on a fourth data point. Okay, and I will get to the spreadsheet here in a minute. I'm going to show you a spreadsheet. We can add a fourth data point very quickly to get a third degree interpolating polynomial. Now where you've got one more term, this one right here, and where this thing here would be a third divided difference. So I'm adding on an x3, and there's a corresponding function value, f of x3. I add on just one more term to get this new interpolating polynomial, which will be third degree for 4 data points. And that third divided difference is a divided difference of second divided differences. By definition, it's this. Now, if you really want to, you could ultimately write this in terms of the zeroth divided differences. I did take the time to do that. It's kind of a mess. There is the expression in terms of first divided differences, and yes, one more. Here is the expression in terms of zeroth divided differences. Fractions within fractions within fractions. And I went ahead and used the square bracket notation here, though I could have used parentheses. Okay? I decided to go ahead and do that. You don't have to. Let's say our x3 data point, which is really our fourth data point, is 813. The updated table looks like this. Okay? Notice that this part of the table is the same as before. Okay? So I'm adding on x3, a fourth node, 8. Its function output equals 13. It's giving me a new part of the table. But this part's the same as before, if I keep the order of those things the same. Let's check these other numbers. Well, maybe you want to check it with your calculator here. Where does the 2.5 come from? It's a first divided difference. In other words, it's a divided difference of zeroth divided differences. It's 13 minus 8, all divided by 8 minus 6. That'd be 5 over 2. 5 halves is 2.5. What about this number? It's a second divided difference. It's a divided difference of first divided differences, these two, divided by this difference between these two nodes. Notice the symmetry. This is halfway between these nodes. That helps remind you that you want to divide by this minus this. So 2.5 minus 1 is 1.5. 1.5 divided by 8 minus 4 is 1.5 divided by 4 is 3/8 is 0.375. Finally, this number that's the same as 1/24. It comes from this minus this divided by 8 minus 2. This difference is going to be 0.25, 1/4, divided by 6 is 1/24, is 0.0416 with the 6 really repeating, but then I'm rounding. So this is giving us a third degree interpolating polynomial. This number will be the x cubed coefficient. The x cubed coefficient will be 1/24. But these things in general are not the other coefficients. In fact, if you simplify it, here's what you get. Okay, that might be worth you taking the time to check as well. Third degree, it's going through all 4 data points, and if we plug in 4.5, we get this approximation. If you've got more data, you would assume this, at least if your function's well behaved, this is probably a better approximation than the second degree one. Is it guaranteed to be better? No. It's only probably better if your function is nice. It's not doing anything unexpected. And here's the graph. Okay, you can see the red graph is a cubic. It's going through all 4 data points, and here's our approximate one. 4.5, 6.33. Need another breath. All right, let's talk about some generalities here. As well as I got to get to the spreadsheet here. I'll make sure I do it at the end of this slide. And well, maybe we should do it now. Let's do the spreadsheet now. So let's first program it based on the 3 nodes. The 0th divided differences are the function values, 5, 6, and 8. Oops, don't put the 8 there. Put it there. First divided differences. We don't need, like we did with Neville's method, to know what x is. Okay? We do this because we're really after the polynomial here. Minus this, all divided by this minus this. 0.5, copy and paste that down here. We get our 1. For the second divided difference, do this minus this, all divided by this minus this. Notice again, these are, in both cases, based on how I've structured things, these things are equally spaced from this line. These are 1 cell above and below, and these are 2 cells above and below the line that this thing is on. Forgot my parentheses. There we go, there's the correct answer. Now let's add on our 4th data point. x3 is 8, function value there is 13. You can copy and paste this one down, copy and paste this one down, and finally do our 3rd divided difference. This minus this, all divided by this minus this. Once again, these are equally spaced across this line. And there's our 1/24. Okay, so there's the spreadsheet implementation. Turns out the nodes actually don't matter. It also would not matter. The method still applies if they were unequally spaced. Though, of course, for our example, we'd get a different answer if we did unequal spacing, because it would be a different problem. If we're going back to using, say, the original nodes, but just reordering them, you can then get a different table and different coefficients for the Newton form. But when you simplify the final polynomial, it would be exactly the same and give us the same approximation when we plug in x equals 4.5. So here I have switched around the order of the nodes. They're not in numerical order. I made the 0th node 6th, the 1st node 4, the 2nd node 8th, and the 3rd node 2. And there's the corresponding function values, which are also 0th divided differences. You should take the time to pause the video here and check these other numbers. And then the upper diagonal from upper left to lower right here, these are going to be the A0, A1, A2, A3 in the Newton form, but the Newton form is different in this case. Notice it's not an x minus 2 there, it's an x minus 6. Its coefficient is 1 because that comes from this one right there. The 8 goes right there. 0.375 is times x minus 6 times x minus 4. Notice 6 is the 0th node and 4 is the first node. And then the 1/24th, which is the x cubed term, as it has to be the same as before, gets multiplied by x minus 6 times x minus 4 times x minus 8. X minus x0 times x minus x1 times x minus x2. If you simplify it though, it simplifies to the same thing as before. This is the exact same cubic as before. Okay, I didn't have you write that down. Maybe you want to write that down now, just so you know what the answer is, but you should take the time to double check that. Again, this decimal is an approximation to the true A3, which is truly 1/24th. And the 0.375 is 3/8. Take another breath. Boy, this is a tough topic, okay? I hope you're hanging with me here. Still important things to talk about, including Newton's forward difference formula. We're almost there. We're getting in the home stretch here. Divided differences in general. Given any n plus 1 distinct nodes, not necessarily ordered from least to greatest. And I would also say, but forgot to say, not necessarily equally spaced. And corresponding values f of xi. The 0th divided differences are the function values. The first divided differences are these things, where I is either 0 or 1 or 2 up through n minus 1. The second divided differences are these things. They are divided differences of divided differences. And the ordering, what I've done here is I've emphasized the ordering doesn't matter. Now for this one, I can rewrite this fraction in the opposite way in both the numerator and denominator and use this notation for it. The order doesn't matter. Same thing with this one. I once again switch those around. It even wouldn't matter. I even could put the x of I plus 1 in the first spot. It would take some proof that you're going to get the same thing, but you would. It's pretty amazing. Recursively define the kth divided differences by this one. Notice I've got xi through xi plus k in there. That's a kth divided difference with k plus 1 numbers inside the square brackets as a divided differences of k minus 1th divided differences. These both have k minus 1 terms in them, divided by the extremes. But once again, if you reorder these and use the same definition, amazingly you get the same answer. That takes proof, and I'm not proving that. But amazingly you get the same answer. All right, now we're on to our final topic, Newton's forward difference formula. It's going to go fairly fast here. Let's go back to the 3-point interpolation example. Note that the nodes are in consecutive order there and equally spaced. x0 was 2, x1 was 4, x2 was 6. Going to let h be delta x, the difference between the nodes. That happens to be 2, right? 4 minus 2 is 2, 6 minus 4 is 2. We call that h. Note that 4.5 is 1/4 of the way from 4 to 6. I use this kind of phrasing when I talked about Neville's method. I could also say 25% of the way from 4 to 6. In other words, 4.5 could be thought of as 4 plus 25% of the way from 4 to 6, because 6 is 4 plus 2. 2 is our h. I'm going to also write that like this. I would like to also write this in terms of x0, which is 2. 4 is 2 plus 2, 2 plus h. So I can also write this as 2 plus 1.25h, because 4 is 2 plus h. h plus 0.25h is 1.25h. Right? You can double check this as well by plugging 2 in here. 1.25 times 2 is 2.5, plus 2 is 4.5. In general, this is going to be represented as x0 equals s, x0 plus s times h, where h is the delta x, and s in general is not exactly a fractional amount between 0 and 1, but you can relate it to a fractional amount, which is what I was doing here. In a sense, 4.5 is 125% of the way past from 4 to 6, if you think of 100% distance as being 2. x0 happens to be 2 here, s happens to be 1.25, and h happens to be 2. Now these are all important numbers. x0, s, and h are all important, but I really want to focus in on the s and the h here. And really in terms of the s ultimately as your variable, so to speak. Therefore, I can think of p of 4.5 as p of this, which is p of this in general, which now I can go back to the other equation involving the Newton divided difference formula, where when it's in the form a0 plus a1 times x minus x0 plus a2 times x minus x0 times x minus x1, etc., the a's are these divided differences. And notice this is x, which is x0 plus sh right there, minus x0. This thing right here is our x that we are plugging in, just written in a different form. Then I have the second divided difference. This thing right here is x minus x0. This is also x minus x1. Now what I can do is I can also replace x1 with x0 plus h. And write this in yet another way. That's an x0 plus h. Focusing on, well, the fact, first of all, that the x0's cancel here and here, and I get s times h. That matches this. So this is f of x0, the 0th divided difference, plus s times h times this first divided difference. It comes from there. And then here I have an s times h times s minus 1 in parentheses times h. The two factors of h, well, this cancels here and here to give you s times h. And when you replace this x1 with x0 plus h, the x0's cancel, and this all simplifies to sh minus h, which is s minus 1 times h. It's supposed to be an s there, not a 5, which is what you see here. Now, it's not completely obvious, the next step that I'm going to show you, unless you were thinking about higher degree situations. But you certainly can think of s times h as s choose 1 times 1 factorial times h. What? Where'd that come from? Remember that in general, s choose k even when s is not a whole number. Well, okay, let me say it this way. When s is a whole number, is s factorial divided by k factorial times s minus k factorial, and my dots are not coming out here. And that can simplify to, well, s factorial can be written as really s minus k factorial times s minus 1 times s minus 2, etc., down through, those are supposed to be dots there. Sorry this is taking so long, but I think it's important. S minus k plus 1. That gets multiplied by s minus k factorial on the top. And then the s minus k factorials on the top and the bottom cancel. So I don't have any more on the top or bottom. I have a k factorial on the bottom. Initially, you want to imagine s being a whole number here when you do this. But when you write it this way, s doesn't have to be a whole number. And that's what I'm trying to emphasize. This expression right here is this thing that I circled with k equal to 1. 1 factorial is 1. So it's really just this product, which is what I have here. S, when k equals 1, I just get an s, an s over 1 factorial. When k is 1, negative k plus 1 is 0. Are you with me? So this all simplifies to just an s when k is 1. Divided by 1 factorial. If I want these things to be equal, I want to imagine multiplying by 1 factorial as well. Now 1 factorial equals 1, so you really don't have to write this in this way, but it generalizes, so it's worth doing. It generalizes in particular at the next term. S times s minus 1 is the same as s times s minus 1 over 2 factorial times 2 factorial, which can be thought of as s choose 2 times 2 factorial. Where again, we can use this choose notation, not thinking of it as a way you might have done in discrete math, but in this way, even when s is not a whole number. And we still have 2 h's here, we still have an h squared. If you plug in s equals 1.25 into this thing, you should double check that we get all this. And this does simplify to 6.40625, our quadratic approximation to the data when x is 4.5. I know that's really confusing. It's probably, even though that was really long, I didn't want it to be that long, it's worth probably watching again. X is 4.5, we're trying to approximate the function at 4.5. You want to relate it to this notation, you want to find s that makes this equal to x is 4.5 based on this h. You want to write it this way, you want to plug the numbers in and see that you get the same final answer. This is perhaps more easily computable in programs like Mathematica, and maybe we'll see that in lecture 21. Is this the last slide I'm forgetting? There might be one more slide after this. Yeah, okay. Almost the last slide. Now let's do the 4-point example. I will go quicker through this one. Again, note that the nodes are consecutive and equally spaced. Okay, that is important for this formula to work. I forgot to mention that. H is once again still equal to 2. As before, 4.5 can be thought of as x0 plus sh, where s is 1.25. The formula with the third degree polynomial is just a one-step generalization of the previous one. So I'm going to skip over these steps, other than just to say that here I have a third divided difference. And notice I'm subtracting x1 and x2 here and here. And if you simplify it, the one more term you add is s choose 3 times 3 factorial times h cubed times a third divided difference. Now again, you may wonder, why do we bother writing it this way with the combination and the factorials? You wouldn't have to. I mean, you could write it more this way. It is more compact, especially when you have more terms in your product up here. It is more compact. You might say it's more programmable in things like Mathematica. Plug the numbers in, you get the same final answer. You should take the time to check that. All right, now we're on the last slide, believe it or not. In general, when the nodes are arranged consecutively with equal spacing h, you can write this. Notice I am using ... notation there, which is fine still. But you can also use combination notation and factorials to write it this way. It's the same thing, just different notation for the same thing. But you can even use this when s is not a whole number in both spots. In the next lecture, I will explain this can be written in a different way. Why it can be written in a different way. It can be written this way, where this part here gets replaced by this symbol here, and that delta to the k power, is it really a power? It depends on what you mean by power. It's really an iterate. Is an iterate of something called the forward difference operator for sequences. Pn is a sequence. Delta of Pn is a new sequence defined by this equation for n equals 1, 2, 3, etc. If the Pn sequence starts with P1, then you get P2, then P3, etc. This gives you a new sequence. You can apply this delta operator over and over again to get powers of it. So I'm going to explain why this is true in lecture 21, as well as talking about Newton's backwards difference formula. Assuming you've watched this lecture, so I'm not going to redo everything in this lecture, and that you've taken some time to understand it. And I also hope to talk about Hermite interpolation some in the next lecture. I think overall focusing more on using technology rather than algebraic reasons for things. If you stayed with me this whole time, thanks for watching.